Hello everyone. In this video, we are going to perform machine learning, and in order to perform machine learning, we are using a data set called as the customer churning prediction data set. So basically in this data set, we are going to predict if a customer will exit the bank or not. And in order to predict if a person is going to leave a bank or not, so basically we are classifying a label, whether if it is yes or no. And in order to deal with such a use case, we use machine learning models like the classification models instead of the regression models where we predict a number. But over here, as we are predicting a label, we are going to use machine learning models which are used for classification. And in order to start working on this project, we have to begin with imports. And as you can see over here, we have imported a few libraries, and in the beginning the first import over here is the pandas. So pandas is a Python library which will help us to create data structures, and not only creating data structures, pandas will also help us to manipulate those data structures. And what we do is we begin our data set, like we load our data set with the help of pandas, where we use pd.read underscore csv, as you can see over here, and it is done with the help of pandas again. So this library will basically help us to work on our data frame and manipulate our data frame. And then the next import over here is the NumPy. So NumPy is a Python library which is used for working with arrays. So NumPy will help us to work on arrays, and at the same time, when it comes to NumPy, NumPy actually stands for numerical Python. And not only working with arrays, NumPy also has domain over algebra and matrices. So after our NumPy, the third import over here is Seaborn. So Seaborn is nothing but it is a visualization library. So it will help us to visualize statistical graphs. All right. And data visualization library is done with the help of matplotlib in Seaborn. And then over here, our next import is matplotlib. So matplotlib is nothing but a plotting library, and it will help us to just create plots. And then over here, you can see that we have imported warnings. And then we have used this warnings.filter warnings ignore. So what this piece of code will do is that it will help us to avoid the warnings that we get when we run our machine learning models. So basically we get some warnings usually when we run our model. So in order to avoid those warnings, we import warnings and ignore those warnings using warnings.filter warnings ignore. And then over here, our next imports are as follows. From sklearn preprocessing, we have imported label encoder. So what label encoder does is that whenever we have a data frame which has a column, let's say, which is of categorical type, let's say we have a color column which has red, blue, and all those colors mentioned in it. So what we do is with the help of label encoder, we convert those categorical data into numerical ones, and we assign a particular number for that particular column. All right. So red, blue, green. Let's say we have three colors. They will be converted into 0, 1, 2 or something like that using the help of label encoder. And then our next import over here is from sklearn model underscore selection. We have imported train test split. So what train test split will do is that train test split will help us to divide our data into training and testing part, and we can use the training part for training our machine learning model, and then we have our test, so we can compare the model using the test data. So this is what train test split will do. And then in order to apply machine learning models, as I told earlier, it is not a regression problem and it is a classification problem. So all the imports over here, all the model imports are classification in nature. We have imported logistic regression, and then we have imported navy base, and the next import over here is the decision tree classifier, and then we have imported random forest classifier. Then we have KNN model over here, and we are also going to use support vector machine. And in the end, we are using a model called as the XGBoost. classifier over here. So this is our XGBoost. And then in order to evaluate these models, we are going to use the help of evaluation metrics such as accuracy score and then area under curve, AUC curve, AUC confusion matrix, and then we are going to use ROC, AUC score, ROC curve, and recall score. So these are nothing but our evaluation metrics, which will help us to see how well our model is performing. And let us see what these models over here mean. So as you can see over here, the first model is logistic regression. And what logistic regression does is that logistic regression is a technique for modeling the probability of an event. Just like linear regression, logistic regression will help us to understand the relation between one or more variables and a target variable. So this logistic regression is used for classification problems, and the basic idea of logistic regression is to find a relationship between features and probability of a particular outcome. So after that, we have our Navy-based model over here. So Navy-based classifier are nothing but they are a collection of classification algorithms based on the Bayes theorem. So it is not a single algorithm, but a family of algorithms where all of them share a common principle, that is, every pair of the features being classified are independent in nature when it comes to the Navy-based model. Then after that, we have imported decision tree classifier. So what decision tree does is that, so first thing first, decision trees are again used for both regression and classification. When it comes to classification models, we use decision tree classifier. And when it comes to regression, we use something called as a decision tree regressor. So it works for both. What decision tree really does is that it will break down a data set into smaller and smaller subset data sets, while at the same time associated decision trees are created. And the final result is that we get a decision tree with decision nodes and leaf nodes. So after that, we have random forest classifier. So what random forest does is that, again, random forests like decision trees can be used for both regression and classification problems, and it always gives a higher accuracy compared to decision trees. So decision trees are prone to overfitting, unlike random forest classifier or random forest regressors, which don't overfit and give us a higher accuracy score. And then next thing is we have imported the KNN model or K nearest neighbors classifier. So KNN is one of the simplest machine learning algorithms. Again, this can be used for both regression and classification problems. And KNN algorithms use data and classify new data points based on the distance function. So again, this can be used for both regression and classification problems. And then we have imported support vector machines. So support vectors, what they do is that support vectors are nothing but they are data points that lie closest to the decision surface or the hyperplane. They are the data points most difficult to classify, and support vector machines are used for classification problems. And then we have XGBoost. Again, in XGBoost, we have both regressor and classifier. So XGBoost can be used for both. We have XGBoost regressor and XGBoost classifier over here. So XGBoost is a popular and efficient open source implementation of the what we call the gradient boosted trees algorithm. So they again, like random forest, give us a higher accuracy. And in order to compare how these models are performing, we do it with the help of evaluation metrics. So evaluation metrics will allow us to compare each model and come to a conclusion like which model performs better than the other. And the evaluation metrics that we are going to use over here can be seen in this import. We have imported accuracy score, AUC curve, and then we have imported confusion matrix. And these all imports are nothing but evaluation metrics which tell us how well a particular model is performing. And as you can see over here, we have accuracy score. So when it comes to multi-level classification, this function computes subset accuracy, and the closer this value to 100, the better the model's performance. And then we have something called as AUC. So AUC stands for area under curve, and it is nothing but a measure of the ability of any classifier to distinguish between the classes, and it is nothing but it is used as a summary of the ROC curve. And even this, the higher the value in a AUC, the better the performance of the model, and the higher the accuracy, it is easier to distinguish between the positive and negative classes. And then we have another evaluation metric over here, which is our confusion matrix. So confusion matrix is a table that is often used to describe the performance of a classification model. So whenever we have a classification problem, only then we use confusion matrix. We do not use this particular evaluation matrix in regression model. And after that, we have ROC curve. So ROC curve stands for receiver operating characteristic curve, and it is nothing but a graph which will show the performance of classification models at any given classification threshold. So this curve will basically plot two parameters. One is the true positive rate and the other is the false positive rate. And then we have our last evaluation metric called as the recall score. So when it comes to recall, recall is nothing but a ratio between true positive divided by true positive plus false negative. And this recall is intuitively the ability of a classifier to find all the positive samples. The best value is 1 and the worst value over here is 0. All right. And so these are all our inputs that we are going to use in order to run our machine learning models. And over here, as you can see, in order to start working on our data set, the first thing that we have to do is load our data set. And so what we do is we read the data set first. Um, and again, as I told earlier, we do it with the help of pandas. So we use this line over here, pd.read underscore CSV. So CSV over here is nothing but the type of file. So when we work on Excel, we use this read underscore CSV. And over here, this is the file name called as churnmodeling.csv. And we are reading the dataset using this line. Then in order to view our data, what we do is we load the data. So basically we read the data and saved it in DF. And when we use DF, this is how our data set looks like. So as you can see over here, we have row number, customer ID, surname, credit score, geography, gender, age, tenure. So all these columns are called as independent. Okay, they are independent in nature. And over here we have exited. So this is dependent. This is nothing but our target column, and we are going to predict this particular column with the help of machine learning models. All right. All right. So in order to start working on our data, the first thing that we'll do is that we'll have to understand the data. And in order to do data understanding, what we do is that we use some functions. As you can see over here, the first function that we have used over here is the df.shape. So what this does is that when we use df.shape, df.shape will display us the total number of rows and columns present in our data set. And as you can see over here, there are 10,000 rows. So the first value is the number of rows, and the second value over here is 14, which is nothing but the number of columns. So there are 10,000 rows and 14 columns in our data set. And then the next function that we have used over here is the info function. So when we use df.info, there are two things that are displayed about the data set. One is the presence of null values, and the other is the data types. So this will display us two things. One is the presence of null values. So as you can see over here, here we can see that the total number of rows is 10,000, And over here, all these values are matching with these values. That means there are no null values present in this particular data set. But when it comes to a scenario where, let's say we have a mismatch over here between these and these values, let's say we have 999 over here, that means one missing value is present in that particular column. So basically we can say that there are no null values in the data set for now, as these values are matching with these values over here. And then the next thing is that it displays us the type of data present in that particular column. So as you can see over here, we have row number, and this is of integer type. So there are all integer values over here. So it will display us the integer type over here. But when it comes to surname over here, it is of object type, as you can see over here. And wherever we have decimals, it will display us a float. So here we have balance. As you can see over here, it displays as float. So it will display us two things. One is the presence of null values. The other is the type of data present in the data frame. And in order to get a clear picture, if there are any particular null values present in a particular column, we can also use a function called as df.isNull.sum. So it will displays all the it will display the total number of missing values present in the particular data set. So as you can see over here, a 0 indicates that there are no null values present in that particular column. So we have zeros in all the columns. That means that there are no null values in this particular data set. And we can go ahead and see the types of columns that are present in the data set over here. So as you can see over here, what we have done is that we have taken the column name exited, and as you can see, what value underscore counts shows us is that it will show us all the types of data that is present in that particular column. So over here you can see that in that particular column exited, there are around 7,963 zero values, and there are 2,037 ones present in that particular column. And the next thing over here is we have used the describe function. So what a describe function does is that it will display us all the descriptive statistics of that particular data, including mean, standard deviation, and at the same time it will also show us the minimum and maximum values. So wherever we have numeric values, only at that places we can use the describe function. So let's say we had a name column over here, the surname column. So this surname will not have any column here. As you can see, this will only work for numeric values. And as you can see in this particular row number column, the minimum value is 1, and the maximum value present in this row number column is 10,000. And at the same time, the mean of that particular column is as follows. As you can see over here, it's 5,000. And at the same time, this is the standard deviation of that particular column. And when it comes to age, we can see over here in that particular data set, the minimum age is 18, the maximum age is 92. So this goes throughout this particular data. So wherever we see these values, they will display the descriptive statistics of the data set only for the numerical values present in that particular data set. Then the next function that we have used over here is the df.nUnique. So what this function does is that it will help us to count all the distinct observations, and it will return series with a number of distinct observations in that particular data set. All right. Then over here, what we have done is that we have used df.columns. So what this will do is that it will display us all the column names present in that particular data set. So over here, as you can see, these are all nothing but the column names. All right. And then this is the basic data understanding that we have done. But in order to have a depth uh, understanding, what we do is we have to do something called as data visualization. So this technique will help us to get a better insight about the data, and we can understand the data more with the help of visualization. And as you can see over here, we have used pair plot. So this is how a pair plot looks like. We have given the data as df. So this is our data frame. And as you can see over here, these are all nothing but scatter plots. So on the x-axis, as you can see over here, we have a row number. Here we have customer ID, credit score, and all these columns over here. These are all the column names. But the y-axis is going to remain same throughout these scatter plots. So as you can see here, this is the row number and exited. And again, we have customer ID and exited again. So the y-axis is going to remain same throughout these scatter plots. The only changes are going to be on the x-axis. And let us go ahead and look at another scatter plot over here. Over here you can see is active member. So this is going to remain same throughout all these scatter plots. Again, the x-axis is going to change. All right. And this pair plot has displayed as all the scatter plots, all the possible scatter plots present in the entire data frame. All right. The next visualization over here, again over here we have printed the column names, and this is the df.head. This is how our data looks like as we saw earlier. And then what we have done is we have used another visualization technique over here. We have used bar plot, and as we can see over here on the x-axis, we have taken the geography, and as you can see, we have France, Spain, and Germany over here. And then on the y-axis, we have taken the estimated salary, and then we have given a key over here, which is the gender. So female are displayed by the light shade over here, and the male gender is displayed by the dark shade over here. And this is the color. The color can be changed. Here we have used the teal, and then this is the data. So data is nothing but our data frame. And as you can see over here, uh, Germany has the highest estimated salary for the female gender, followed by the male gender over here. So this is how the bar plot looks like when we take geography on the x-axis and estimated salary on the y. And wherever we mention the u, that will be turned into a key over here. And then the next visualization over here is again a bar plot. Over here, what we have done is that we have taken the age on the x-axis, and then we have taken their estimated salary on the y-axis over here. And as you can see over here, the age, which is 84. So the age 84 has the highest estimated salary over here, and then the lowest salary that we can see over here is for the age which is 88 in number. So this is the bar plot for the age and estimated salary. Again, we can also use u over here. Again we can use gender, and we will get a key. So u can be used over here in order to get which gender of which age has the highest estimated salary. And then over here, what we have done is that we have taken the age again and exited on the y-axis over here. So these are the age, but over here the y-axis has been changed. Previously it was estimated salary. Now we have taken exited on the y-axis, and you can see over here that the age groups are as follows over here. And the next visualization over here, what we have done is that we have taken gender on the x-axis and estimated salary on the y to find out which gender has the highest estimated salary. And over here we can see that this particular bar, which belongs to female, has a higher estimated salary compared to the male gender. Then we have used the gender on the x-axis and balance on the y. We have mentioned a color teal, and over here you must notice that we have given 10 command. This is nothing but the figure size. We can change these numbers, so it will change the size of the particular visualization. And over here you can see that we have used something called as x-ticks rotation equal to 90. So what this will really do is that it will rotate this particular label as you can see over here. And when we remove this particular line, we won't find this rotation over here on the label of the x-axis. So whenever we have a lot of values on our x-axis, we can use the x sticks over here and we can rotate the label. As you can see over here in this particular visualization, if we don't use this particular x sticks, then all these numbers are going to overlap and create a confusion. So this is what x sticks does. And when we come to the other visualization over here, we have taken age on the x-axis, y on the y we have taken the estimated salary, and then we have given a u, which is the gender, and here it will display as the keys. And in this particular bar plot, blue over here stands for female, and orange is for the male gender. And as you can see over here, for the age 84, again, the female gender has the highest estimated salary, followed by the male gender over here. All right, let us go ahead and see our next visualization. And over here, we have taken age on the x-axis, and on the y, we have taken number of products. And over here, we can see that the age and the ages 83 and 84 has the lowest number of products. And when it comes to ages that belong to the 80, 82, 85, 88, these have the highest number of products by that particular age. And then in the next visualization over here, we have taken a number of products on the x-axis. And as you can see, there are only four number of products over here. And then we have taken the estimated salary on the y-axis. And this is how our visualization looks like. This is our bar plot for number of products and estimated salary. And in the next visualization, what we have done is that we have taken age on the x-axis, and on the y we have taken the tenure of that particular age group, and then we have given a u again, which is the gender. And as you can see over here, again, ages that belong to the age group 80 and 85 have the highest tenure, and the male gender, which belongs to the age group 80, has the highest tenure compared to the female gender. And over here, when it comes to the age group 85, the female gender has the highest tenure compared to the male gender. So this is how our visualization looks like when we take age on the x-axis and tenure on the y. Over here, what we have done is that we have taken the column name is active member on the x-axis and the geography or the location on the y. And as you can see over here, uh, the uh, the country Spain has the highest uh, active members, and the active members belong to the country Spain over here. And over here, as you can see, the orange bar belongs to the male gender, and the blue belongs to the female. And the lowest active members are found in Germany, and the females have the lowest active members in Germany. So this is how the visualization looks like. Let's move to the other visualization. And over here we can see that uh, we have taken active member on the x-axis and exited column on the y-axis over here. And as you can see over here, the number 0 over here has the highest exited bar over here. And next, let's move to the next visualization over here. What we have done is that we have taken these active member on the x-axis and their estimated salary on the y. And as you can see over here, orange belongs to the male gender and blue stands for the female. And then we have used u over here, and that's the reason why we have a key. And over here, what we have done is that we have taken the has card column on the x-axis and exited column on the y. And again, we have given the u as gender. And again, blue is for female and orange is for male. And over here, we have done a similar visualization as before. We have taken the hash card on the x-axis, and on the y-axis we have taken the geography, and the hash card is highest for Germany for the male gender, and the lowest is for geography of Spain for the male gender. And then the next thing that we have done is that after we have understood our data and after we have done the visualization, the next thing is that we have done label encoding. So what label encoding does is that wherever we have a column which is categorical in nature, label encoding will convert those particular categorical values into numerical ones. So over here we have three uh, countries in a particular column, which is the geography. Here we have Germany, Spain, and France. So we have taken this particular column in the categorical column, and then at the same time we have also taken the gender. So male and female are encoded with the help of label encoder. What we have done is that we have used this fit underscore transform, and then we have converted these columns into numeric ones. As you can see over here, we have geography and gender, which were previously of object type, and now you can see that the geography is converted to integer type, and then again gender, which was of object type, is now converted to integer. So this is done with the help of label encoding. We have converted all the categorical data into numeric data with the help of label encoding. The next thing that we have done is we have displayed all the columns again. It can be done with the help of df dot columns, or it can also be done with the help of df dot keys. And these are all the column names. And what we have done next is that we have dropped a few unnecessary columns. Like we have dropped the row number, we have dropped the customer ID and surname. So these are not going to help us in our machine learning models. So what we have done is that we have dropped these column names with the help of a function called df.drop. So as you can see over here, this is the we have given access equal to 1 and place equal to 2. So what this code does is that it will drop that particular column and remove it from the data frame. And then the next thing is that we have created a distribution plot. So what a distribution plot does is that it will show us how the data is distributed in the data frame, whether the data is skewed in nature or not. That can be found with the help of distribution plot. Over here, we have given two rows for our distribution plot, and then in one particular row, we have given 5 columns. As you can see over here, we have 5 columns and 2 rows. The next thing is that we have given the figure size, which is 16,4, and then we have given the column names, and over here we have index equal to 0, and then we have created a distribution plot. And as you can see over here, our data is distributed in the right way. But whenever we find out that our data is distributed in a way where all the distribution plots show us skewness, then we can do something called as the log transformation, which will transform the data and change the data into normal distribution. But for now, we can say that the data is correct and we can go ahead with our data and we can perform splitting. So what we do is before we split our data into training and testing parts, we basically split our data into independent and dependent columns. So we basically remove the target column from the data frame. And as you can see over here, what we have done is that we have dropped the target column, which is the exited column. Okay. And then we have this data frame over here without the target column. And the next thing is that we have saved the target column on Y. So as you can see over here, when we use x dot head and y dot head, in the x we see that we have all the independent columns, and when we use y dot head, we can see these are all our target columns or the dependent column. And the after we split our data into independent and dependent columns, what we do is that we split our data into training and testing parts. As we saw earlier, we imported a train test split, and this is the code related to that import. So what we have done over here is that we have split our data into training and testing part. Over here you can see the test size is 0.2. So what this really means is that around 80% of the data will be used for training purpose, and the remaining 20% of the data is going to get used for the testing purpose over here. And if we change the value from 0.2 to 0.3, then what really happens is that the training data will change into 70%. So 70% data will be used for training purpose, and the remaining 30% of the data will be used for testing purpose. So this is what that value does. And this value can be 0.2 or 0.3. And over here we have used 0.2. Then we have given a random state. So what this random state does is that let's say among five people, two people use the same random state, then those two people are going to get the same results compared to the other three. So this is what random state does. And then over here we have printed the xtrain dot shape, xtest dot shape, ytrain dot shape, and ytest dot shape. And these are all the shapes. Okay. Then we are now ready to perform machine learning. And as we talked earlier, we imported models like the logistic regression. So what we have done over here is that we have fit the model on trained data, and as you can see over here, the logistic regression is saved in log underscore rank. And then what we have done is that we have predicted this model on the training data. And as you can see over here, we have used logistic regression dot predict on X train, and then we have printed the model accuracy on train. And over here, this is the accuracy score, which is our evaluation metric, and we'll use this accuracy score to compare with the other model. And then what we have done is that we have predicted the model on test data. And as you can see, we have used logistic regression or predict on X test. And then what we have done is that we have printed model accuracy on test. And then this is the accuracy score on the test data. And then over here, you can see that we have used the print command over here. So what this will do is that it will create a dotted line which will repeat for 50 times. Okay, so this will basically create a dotted line. And then what we do is we have used the ROC curve or ROC accuracy, which will tell us which is nothing but another evaluation metric. And then we have used a confusion matrix. And what we have done is that we have printed the confusion matrix on train, and then we have printed the confusion matrix on test data, and then we have calculated the total number of wrong predictions made by the data made by the machine learning model. And over here, this is the wrong prediction made. We have calculated all the wrong predictions that were made out of the total predictions with the help of confusion matrix. And then we have also used another evaluation metric over here, which is the kappa score. All right, and as you can see over here, the logistic regression gave us a model accuracy on train, which is 0.78, and then the model accuracy on test is 0.8, and the total number of this is the ROC score as well as the ROC score on train and test. Then this is how our confusion matrix looks like. As you can see over here, the total number of wrong predictions made by the model 400. So this will show us that 400 predictions made by the model are wrong, and over here this is the total number of predictions made by the model. And as you can see over here, this is the kappa score, which is 0.05. So this model is not very good. Let us compare it with the other models, and we'll compare all these models evaluation metrics to find out which model performed very well. The next model over here is the Navy based classifier, and the Navy based classifier over here, we have done the same thing. we have used the Gaussian navy base over here, and we have fit this model on X-train and Y-train. We fit this model on the train data, and then what we have done is that we have used navy base dot predict on train X-train. So and then we have printed the model accuracy on train, and this is the accuracy score, which is our evaluation metric. So first we have fitted the model on X-train, Y-train, and then we have predicted the model on X-train, as well as we have predicted the model on X-test. So over here you can see that we have printed the model accuracy on test as well. Again, our evaluation metric over here is the accuracy score, and then we have used the ROC score over here, and we have printed the ROC score on train and test as well. And this is again the same print command over here, which will create 50 dotted lines. And then we have the confusion matrix over here, and this is the confusion matrix on train and confusion matrix on test. And then again we have predicted all the wrong predictions, and using this confusion matrix we have calculated the total number of wrong predictions over here. And this is the kappa score again, and as you can see over here, the model accuracy on train is 78%, and the model accuracy on test is 79, and the ROC score on train is 52. And again, the similar value can be seen on the test as well. And then this is our confusion matrix, and the total number of wrong predictions made are 417 out of 2000 predictions. And again, the kappa score over here is 0.06. And as you can see over here the model has made 417 wrong predictions, and over here it has made 400 wrong predictions so far. When it comes to navy based classifier and logistic regression, we can say that the logistic regression model has performed well. Let us go ahead and see how the decision tree classifier and random forest classifier have performed. And again we have used the decision tree on X and Y, and then what we have done is that we have predicted the decision tree on train and then X train, and then we have predicted the decision tree on X test, and then we have printed the model accuracy on train and model accuracy on test, and then again we have calculated the ROC score. And over here we have used the confusion matrix again, and out of this confusion matrix we have calculated the total number of wrong predictions made by the model. And again we have used the other evaluation metric over here, which is the kappa score. And as you can see over here, the model accuracy on train is 100%, and the model accuracy on test is 100 again. The ROC score is 100 and on test and train both. Then over here you can see that when it comes to the confusion matrix, we have used the confusion matrix to predict the total number of wrong predictions. As you can see over here, we can see that the number of wrong predictions are 0 out of 2000, and the kappa score is 100%. So people might think that this is the best model, but we have to say that this is not a good model. In fact, this is a bad model, and this is a clear case of overfit. So the decision tree model is overfitting, and that's the reason why we have the accuracy as 100% on train and test. So this is not a very good machine learning model to predict our future values. So we will move on with the next model over here, which is the random forest classifier. Again, the same thing has repeated over here. We have fitted the random forest classifier on X train and Y train. Then we have predicted the random forest model on X train, and then printed the model accuracy on train. And we have used the accuracy score evaluation metric over here. And the next thing is that we have predicted the random forest model on X test as well. And then we have printed 50 dotted lines. We have used the ROC score, and as you can see we have printed the ROC score on train and test. And again we have used the confusion matrix same as before. Confusion matrix will help us to calculate the total number of wrong predictions made by the model, and this is our kappa score, which is nothing but our other evaluation metric. Over here you can see that the model accuracy on train is 100, and the model accuracy on test is 87%. And when it comes to the wrong predictions made in total, here we can see that the total number of wrong predictions made are 248 out of 2000 predictions. And over here you can see that the kappa score is improved, which is 53. That means so far this is a very good model compared to the logistic regression. As you can see over here, 248 are the total number of wrong predictions in the random forest classifier. And when it comes to the logistic regression, over here we can see that 400 predictions were made wrongly by the model. And again, you can see again the kappa score is 0.05. So we can clearly say that the random forest classifier is a better model compared to the other models. But let us go ahead and try other machine learning algorithms as well. We have used the k-nearest neighbors, and again we have fitted the k-nearest neighbors on the x-train and y-train, and we have predicted the k-nearest neighbors on x-train and printed the model accuracy on train. And then we have predicted the k-nearest neighbors model on x-test and printed the model accuracy on test as well. And then we have divided this with the help of print command using 50 dotted lines. And then we have used the ROC score on train and test. And then we have used the confusion matrix. And out of this confusion matrix, we have predicted the total number of wrong predictions made by the model. And then we have used the kappa score over here. And as you can see over here, the kappa score is very less. And the model accuracy on train is 81 and the model accuracy on test is 77. And this is not a very good model again. As you can see, around 460 predictions made by this model are wrong out of the total number of predictions, which are 2000. So this is not a good model. Let us go ahead and use the other models. Over here we have the support vector machine. Again the same thing. Over here we have used a kernel over here which is linear, and we have fit the model on X train and Y train. And then again we have predicted the SVM model on X train, then printed the model accuracy on train. And then over here you can see that we have predicted the model on X test, and this is the model accuracy on test. Then we have printed the ROC score on the Y train and Y test. Then this is our confusion matrix, and over here we can we have calculated the total number of wrong predictions made by the model using the help of confusion matrix. And again we have printed the kappa score. Over here again you can see that the kappa score is very less, and directly we can tell that this model is not good. And over here you can see that the model accuracy is 77 on train and 78 on test, but the kappa score is low. It means that this model is not a good model. And again you can see that the total number of wrong predictions made by this model is 424 out of 2000 predictions. So this is not a good model as compared to random forest classifier, which performed very well. So now we are using a last model over here, which is the XGBoost classifier. And as you can see, we have used the XGB classifier on X-train and Y-train. We have fit this model on X-train and Y-train. Then we have predicted the model on X-train. And then we have printed the model accuracy on train. And then we have printed the model accuracy on test as well. Then again, this is a line that will separate all these evaluation metrics. You will just create a dotted line. Then this is the ROC score on train and test. And we have our confusion matrix. And this is the recall. We have used another evaluation metric over here, which is the recall. And then we have compared and calculated all the total number of wrong predictions made by the model. And then we have used the kappa score over here. And as you can see over here, the model accuracy on train is 95% and model accuracy on test is 86%. And the kappa score over here is 53. Let us compare this with the random forest. Over here we have 266 wrong predictions. And in the logistic regression, I mean in the random forest classifier, the wrong predictions are 248. And over here we have 266. So we can say that the random forest classifier is again better compared to the uh, XGBoost classifier. So the next thing that we have done over here is that we have hyperparameter tuned the model, which is a random forest classifier. As random forest classifier gives us a good score, what we have done over here is that we have used manual hyperparameter tuning over here. So all these parameters over here belong to random forest classifier. We have total number of estimators, minimum sample split, and this is the total number of max features. This is the random state that we have given. So we have given all these values on our own. This is our random values, and using these random values or manual hyperparameter, we can see that the model has performed very bad, as you can see over here, that the accuracy is 81 on train and accuracy on test is 83, and the kappa score has drastically reduced, and the total number of wrong predictions are higher. And as you can see, using these hyperparameters tuning, using the random values in our hyperparameter tuning, we have reduced the accuracy of our model and increased the total number of wrong predictions. So in order to give the correct uh, parameters, what we have done is that we have used a random search CV as well as grid search CV. So these both will help us to give the right parameters to our random forest classifier. And in order to use the random search CV, what we do is that we have to import the randomized search CV from sklearn model underscore selection. And over here we have given the n estimators. So n estimators are the number of trees in our random forest. So here we have given these values over here. The values will start from 100 and stop at 5000, and the total number of values are going to be 10 in number. And then the max features that we have given over here is auto, square root, and log 2. Then these over here are the max depth, and then this is the minimum number of split, and this is the minimum sample leaf. So we have given all these values, and then we have stored all these values in random grid, and we have given all these values over here. As you can see, we have the estimators, max features, max depth, minimum sample split, and minimum sample leaf. And when we print this, when we run this cell, you can see these are all the number of estimators, and these are all the max features, max depth, and these are all the features that we have assigned to this randomized search CV. And then we have applied all these features to a random forest classifier, and as you can see, we have fit this random CV on X train and Y train, and these are all the parameters. And among all these parameters, these are all the best parameters. So from all these parameters that we have given, the random CV says that the total number of estimators should be 100, and minimum sample split should be 14. All right, and this is our randomized search CV, and these are all the best estimators that have to be used by a random forest classifier over here. And we have stored all these random CV best estimators in the best random grid. And the next thing that we have done is we have predicted this on our data. And what we have done is we have used this random grid and predicted on X test. Then we have printed a confusion matrix. And as you can see over here, after using our randomized search CV, our kappa score has now increased, and it has slightly increased. It was 54 before our randomized search CV, but we can compare the slight improvement with the help of the total number of wrong predictions made. Over here, you can see that the number of wrong predictions over here are 243, but when we compare it with the previous random forest classifier, we can see that the total number of wrong predictions made by the random forest classifier were 248. So we can say that there is a slight improvement using the randomized search CV. Uh, as the total number of wrong predictions have reduced from 248 to 243 over here. And now the next thing that we do is we use the grid search CV. And as you can see, we use the grid search CV, and over here we have imported the grid search CV from SQL under model underscore selection over here. And then these are the random CV's best params. All right. Then what we have done is we have created a parameter grid where we have given all these features over here, which is the criterion, max depth, max features, and total number of estimators. And then as you can see over here, these are all the estimators that I've used over here. And then we have used this grid search CV and predicted on a random forest classifier. So all these parameters have been given to our random forest classifier now. And out of them, these are all the best parameters, where criterion is better when it is used as entropy, and max depth is 894. So these are all the parameters. Then what we have done is that we have predicted the random forest classifier again, but now we have used all the grid search CV's parameters. And as you can see over here, that the total kappa score is 54. And again over here, there is a slight decrease in the performance of our random forest classifier, as the previous randomized sort CV gave us less number of wrong predictions. Over here, we can see that the total number of wrong predictions are 246, whereas the randomized third CV gave us the total number of wrong predictions as 243. So what we can say over here is that uh, the random forest classifier has performed well when we use the randomized search CV instead of the grid search CV, and this model can be further tuned, and this tuning takes a lot of time, so it must be done with patience. And again, there is a scope of improvement for this model. Again, it can be increased, but for now, as so far what we have seen is that the decision tree model showed us overfitting problem, and then random forest classifier performed very well. So what we have done is that we had used randomized search CV and grid search CV, and there was a slight improvement in our random forest model using these hyperparameter tuning techniques. And we can hence say that the randomized search CV on random forest classifier gave us a better accuracy, which is 87%, and the total wrong predictions made by the model were 243 by 2000. And when we use grid search CV, the accuracy was 87%, and the wrong predictions made using grid search CV were 246 out of 2000 predictions. And that's it for this